All the term spontaneous means is that a reaction will occur without a continued input of energy, as a car wouldn't spontaneously roll up a hill, but it could roll down one. It may need an initial push to get going, but the point is that it will require no energy to continue going downward.
Most of the time, spontaneous reactions release energy, like the gas as it burns and releases heat, which hurts, actually, when you touch it. This means that the reactions are exothermic. For a long time, many believed that exothermic reactions would automatically be spontaneous and endothermic reactions would automatically be non-spontaneous.
While this is often true, ice cubes like these serve as an indicator against that assumption. If all exothermic reactions were spontaneous and all endothermic reactions were non-spontaneous, these stars would be in good shape.
That's why entropy is important. Entropy is a state function used to measure the extent of energy dispersal. As stated in the second law of thermodynamics, a spontaneous process is one that results not necessarily in the release of heat, but in an overall increase of the entropy of the universe. Typically, the release of heat results in an increase of entropy, leading to the previous misconception.
For example, when I drop this book on the floor, potential energy is being transferred to kinetic energy and therefore released from the book. As the book falls, there's an increase in entropy.
Remember the density demo with the golf ball and the salt? The point of that demo was to show the effect of gradual dispersal of the salt as it dissolved, which was another spontaneous process. Like salt and water, energy works in a similar way. It doesn't like to remain confined in one place, so it instead tries to spread out as much as it possibly can. Releasing energy into the universe facilitates this dispersal.
The law of conservation of energy reminds us that energy cannot disappear, nor can it be created from nothing. However, it can change form and be distributed.
Think of a parent with 3 children. He or she has $5 in ones and wants to distribute the money evenly between the 3 children. Ideally, each child would receive about $1.67. However, since the parent has no change, he or she must distribute the money unevenly.
Like this scenario, energy often distributes itself evenly, but in cases where doing so is impossible, energy will sometimes distribute unevenly.
This is where microstates come in. Microstates are just the ways in which energy can be distributed, or concentrated. The more energy there is to start with, the more there is to go around, and the less likely the energy is to be concentrated. Picture a container that you drop bouncy balls into. The bouncy balls bounce around in the container for a while and then stop in rings that you've drawn on the base of the container. The chances that all of the bouncy balls that you dropped in will end up in the same ring on the bottom of the container is very slim. If you had 30 bouncy balls, chances are they're not going to end up in all the same place.
Now that we've sufficiently restated several very long pages of our textbook, you're probably ready to apply something. Energy dispersal can be calculated with an equation created by the Beethoven of the physics world. Here, Ludwig Boltzmann proves that just as the number of microstates, that is the number of ways in which energy can disperse itself, increases, so does the entropy. This is shown as S equals K times the natural log of W. In English, entropy equals the Boltzmann constant times the natural log of the number of microstates, where K is the Boltzmann constant with a value of 1.381 times 10 to the negative 23rd joules per temperature in Kelvin, and S stands for entropy.
To find natural log on your TI Inspire, all you have to do is press the blue control button on your TI Inspire and then press the button that has e to the power of x on it. This button should have a blue ln over it. On your screen, you should now see an ln and then parentheses.
There's one more thing you should know. Entropy relates directly to temperature. At 0 Kelvin, the entropy is 0. However, if the crystal is under any different conditions, aka pretty much every realistic situation, then entropy can be determined. You have to look at how the crystal is different from the standard of K equals 0. By looking at the entropy gained by converting the substance from 0 Kelvin to the other conditions, you can write an equation to determine S. To determine S, you must measure the energy transferred as heat when you convert from K. Then put this over the Kelvin temperature. This equation shows change in S.
Change in enthalpy equals Q of the reverse reaction over T in Kelvin.
So thanks to everything Anjali and Abigail have taught us, we now know that reaction spontaneity relies on 3 main factors. A reaction is more likely to be spontaneous if energy is given off. That is, yes, it does matter if the reaction is exothermic, but that is not the sole deciding factor, as there are still exceptions. The second factor is the entropy of the universe is increased. And the temperature also, as the temperature increases, the reaction is more likely to be spontaneous because, as you will see later, it's directly related to the entropy. Again, the first and second laws of thermodynamics clearly state that although energy in the universe can't be created or destroyed, entropy can, and it is increasing.
Although you've learned all about the factors of entropy and spontaneous reactions, you still haven't learned of how to combine these factors to definitively state if a reaction is spontaneous. Don't worry, girls. Gibby feels your pain. Thanks to him, we now have a simple equation called the Gibbs free energy equation, and it will immediately determine the free energy released or given off by a reaction.
The equation to calculate the change in free energy is delta G equals delta H minus T delta S. The amount of free energy equals the change in enthalpy, remember that's the change in heat, in energy in the form of heat, minus the temperature in Kelvin, times the change in entropy, which is the change in the disorder of the universe.
Notice how performing this equation requires you to calculate both the change in entropy and enthalpy.
When a pure element is in its reference form, that is like oxygen would be a gas and sodium would be a solid, the standard enthalpy is 0.
For purposes, we will be using the standard enthalpies found in either the back of your textbook or Google.
The change in entropy equals the sum of standard entropies of products minus the sum of standard entropies of reactants. Once you have that wonderful number, determine if the value is negative, positive, or 0. If the value is 0, the reaction is at equilibrium and no further reaction will occur. If the value is negative, the forward reaction is spontaneous. If the value is positive, the reaction is non-spontaneous.
Just a side note, just because a reaction is spontaneous doesn't mean it's always occurring.
As we mentioned at the beginning of this video.
A spontaneous reaction might require an initial burst of energy, just as a car might require an initial push to really get going down the hill. But the difference is spontaneous reactions do not require a sustained input of energy for the reaction to continue. Using values of delta H and S, calculate delta G for the following reaction at 25 degrees Celsius. 2 Pb plus O2 yields 2 PbO. See below for the following enthalpies.